Oh,
Okay. Hello, everyone. My name is Sarah Hu. The other R instructors here are Ella and Jacob. I'm going to talk about ordinations today, specifically making PCA plots. So we're going to make a PCA plot by the end of today. The code is on the BVCN R Studio space and on GitHub and everything. And it's under lesson 8b. Lesson 8A, I don't think it has an A on it technically right now. Liz Suter gave last week. It was really great. And these are starting to be crossover episodes, crossover lessons with the Amplicon group, because they've come through processing the Amplicons, and now they're working in R to work on visualizing some of the results from that. And so today I'm working with the Amplicon data set, looking at ordinations. And what Liz went over last week was really great. And it was looking at ordinations, but from the phyloseq object. And so you're using the phyloseq object and then making ordinations. Today I'm actually doing a little bit of a different approach, but we're talking about a lot of the same things. And I think I use phyloseq a lot, and I also use non-phyloseq. And so I'll talk about that a little bit. And if you're from the Amplicons group, this is lesson 5b in the Amplicons lesson numbers. So go ahead and open up lesson 8, and you want to make sure you're installing those libraries, because there's quite a few libraries to install. I'll share my screen in a second, but that might take a little bit of time. And I'll go over, if you have any questions about which packages we're using today, please chime in or ask questions in the chat. Ella and Jacob are going to be monitoring that for me. All right, so this is actually part of the stuff I'm going to go over today is actually part of a paper that I'm on. And I've listed the citation here. I encourage you to check it out. I worked with a group of people, and we kind of, the manuscript is actually more of an introduction to doing time series analysis with Amplicon data. And I'm going over like a snippet of that. So there's a lot more that paper has to offer. You can go to the GitHub directly even and just look at the different tutorials we have. And it's geared towards time series analysis, but I've just pulled out some of the ordination stuff. And I've modified a little bit of the code to be more in line with what we've done in the BVCN R, specifically with kind of being loyal to the tidyverse. And so I'll go over some of those. And if you're not familiar with that, I recommend looking at those lessons, because I'm not going to go into too much detail about it. Okay, so hopefully you've installed those libraries and the packages, install those packages, and both these lines of code to install those libraries is okay. Right now, we're loading this test data set. It's a diel test data. And this is used in the manuscript as well to kind of go through a couple of different ways to approach time series analysis. And what it was is it was a data set where I had samples from every 4 hours for a period of 3 days, and I'm looking at the microbial eukaryotic community. I'm not going to go too much into interpretation today, but I just wanted to let you know that for background. So this is Amplicon data. By looking at, so what I mean by Amplicon data, it's like kind of a traditional OTU table, and ASV tables, we use those terms interchangeably today because you can put both in, where you have the first column is some kind of unique identifier. And by row, you have the OTU IDs or feature IDs for ASVs. And then across, these are all of my sample names. And then going along with, or corresponding to these OTU IDs and the values in each of these rows is the taxonomic information here. And so this is one where I have taxonomy in one column, and then I have the taxonomy split into separate levels and all this stuff. And we're actually not going to look at taxonomy today, because we're just going to try to make PCA plots. But I wanted to show you this because it's in contrast to what some of the phyloseq, you have to modify your data before putting it into phyloseq, so it's in this type of format. But I often am using data directly in this type of format in R instead of going into phyloseq and working with a phyloseq object. So first, I want to modify this data set so it's suitable for what we're going to do downstream. So I'm using a tidyverse code block here or code chunk here where I have the input data. First, I'm going to remove OTUs that I don't want. And so I'm actually filtering them by taxonomy here, things that are none and unassigned. I kind of did this arbitrarily right now for the purposes of this lesson. And also removing singletons. using mutate to create a new column that sums up all the counts in a row. And if that OTU has only one count, then it's removed in this next column or this next line of code. And then finally, I make a new table where I'm selecting only those columns that end in PM or AM. Okay, so then at the end, I only want a data frame that has only these as column headers and then only this OTU ID, and I'm actually changing it to a row name. So that's all in one chunk of code. So this is what my data frame looks like now, where I have my row names is equal to, remember that's that indexing feature of a data frame, is my OTU IDs, and then each of my columns are the sample names. And then here I'm actually making a taxonomy information, making a key, and realizing now after I wrote this lesson that I actually don't end up using this at all. But this is, again, another feature of what I use. This is just what I do in my own practice of working with OTU or ASV tables, because then I can work with this data without the taxonomy information and use these OTU IDs as unique IDs by row. And then later on, if I want to know about what's going on with this OTU, I can refer back to this taxa key and find that OTU ID here, and then all the taxonomy information that goes along with it. So let's get into why we have to spend some time thinking about data transformations before we do PCAs. And that has to do with the fact that OTU and ASV data are compositional. So what that means is that, this data, we're looking at sequence abundances. And I think if you're familiar with doing any Amplicon work right now, you definitely know of this. And hopefully when you're writing or interpreting this data, you think about this a lot. That's definitely what I'm doing. And your sequence data does not represent true abundances, meaning if you see a signal in a taxa ASV or OTU that's increasing, that means it's decreasing somewhere else in your data. And you can't interpret those values as true abundances. And so there's a lot of things that we need to do to be aware of this. And we rely a lot on like relative abundances, for instance, with OTU and ASV data. But it's really important to acknowledge some of this kind of overarching caveat of the data structure of a tax sequencing data set. I have quite a few references that I've put in here that I highly recommend if you want to learn more about compositional data. They offer a lot of solutions or workarounds. And if anything, I think that there's a lot of really neat stats and packages and R especially that are coming out that allow you to work with compositional data. And I think it's really great. So quickly, Jacob or Ella, do you have any comments about just like intro stats of why we need to do this? Or any questions that have come up? I actually don't. Okay.
Doing great, Sarah.
Okay. So the first thing I'm going to do is actually, so a lot of this, the way my tutorial is going to go today for ordinations is thinking about diagnostic tools that you can do before making a PCA or making the right decisions to make a PCA plot that is the most appropriate way to show your data. And I don't think I have to prove to you that your data isn't compositional, but I want to kind of show another example of how you can look at that, because there's a lot of other data types we work with that are compositional as well. Right, so to think about principal component analysis or PCA, there are a couple of things are happening. And the first one is that, right, you have this complex data set and you're trying to put it into a space where you can visualize it in 2 or 3 dimensions. And you want it to, in that visualization space, you want it to be able to show all the appropriate relationships between all your samples. And with that, the first thing that happens is in your PCA calculations is that you're calculating a data covariance matrix. You're measuring the variability among all the random samples or random points in your data. And then you do a decomposition, Eigen value decomposition of this matrix. And so then you get the Eigen values or the axes of that variance. And those are what we use to determine, we're going to use those today to determine how many axes are appropriate to show your data, likely 2 or 3, and what kinds of things you can do to explore the data structure before you move forward. So the first one is first doing those 2 steps that I kind of mentioned, calculating the covariance matrix, and then pulling out those variances and kind of diagnosing what's going on. So this first line, I'm taking that data frame that I've QC'd, I'm multiplying it to itself and to estimate covariance. And then I'm doing a determinant of the covariance matrix here. And the output is 0. And I have an explanation here, but right, if we have, what we're doing here is we're multiplying all of those PCA axes. And if one of them is 0, which means that there's an axis in here that explains 0 amount of the variance, which we don't want in our data, then if you're multiplying all of them, the product is going to be 0. And so this is the evidence of compositionality in the data. A quick side note for thinking about like R syntax, and this is something that came up earlier in our lessons when the reason I'm able to kind of just use this on its own is that I did that row names and put that OTU ID as row names, and then all of my other data was in a numeric format. So then that's another reason why I kind of stripped that OTU table of all the taxonomy information, just so I have those numerics. So those are the two main points I wanted to bring up with this section. But now I can see that my data is compositional, and that's why I need to think about different types of data transformations. So the first,
Sarah,
yeah.
Are your data no longer compositional because you've done an ILR transform on them?
I haven't done it yet.
ILR.
I'm getting into it now, but I haven't done it yet.
Oh, I thought the dialog rats had already been transformed on line 75. Or am I in the wrong place?
We're not there yet. We're about to go there.
Sorry,
yeah.
my bad.
Yeah, so Jacob has introduced the log ratio transformation, which we're going to do now. And so I think that's the first place that I go to. Maybe Jacob and Ella can comment on what their first step is. We're using the library compositions for this. And the command is ILR or CLR to do an isometric log ratio or a centered log ratio. And right, so we know that the sequence data we're getting is like kind of all over the place, because maybe you've seen some Amplicon data, but what this is doing is it's kind of centering the data around a single point. I think the term here is like a focal taxa or something. And so for instance, the CLR or the centered log ratio, all the values are going to be centered around the geometric average. In fact, I'm going to try to live code one thing really quickly. So I'm going to do the transformation here to walk you through this part, right? I have my input data frame. I am transforming it, so just shifting it or rotating it kind of, and then doing the ILR. This notation here means I'm using the compositions library, and then these two colons bring up the command I can put in. And so this is actually the exact same thing as this because we already loaded the compositions library. But without loading the library, you can actually place it here. I just wanted to show you a little trick, I guess. But after doing this, okay, I'm pretty sure we can do, I'm not sure if this is correct. Can I, no, never mind. How do I select all the columns? Maybe that will work. Okay, that's, let's see. Sorry, hold on. No. I should have looked up how to do this properly, really quickly. Sorry.
I need a comment in there, Sarah.
Oh.
Right, so you want all of the rows from some of the columns or some of the columns?
Yeah, I was just gonna do random. Let me look at, hold on. I didn't think about.
If you just want V1, you could just $sign V1 it.
Yeah, we'll just do V1. So what I'm trying to show you guys is the distribution now of the data. So I'm just pulling out one column here. I'll pull out a column at random actually. Oops. Yeah, so I'm looking at the distributions of my data now. But you see, I'm pulling out random columns, but now you'll see if you look at the x-axis on the plot, that's what I'm kind of interested in showing you guys, is that now it's centered around these values, and it goes from negative values to positive values, and it's centering around 0 actually. And so I'm just pulling out random OTUs essentially and showing you the distribution of them, and so it's not really representative of the entire data set. I think I could quickly melt this data, but I don't think I have to melt. Yeah, so now the data, my point is that the data is now normally distributed. And then I can do names to temp. Oops. All right, I'm going to stop because I don't want to take up too much time because there's a lot of stuff to go over. But the data is normally distributed. I think we'll show that later when we get to a data frame point. But now what I'm going to actually recalculate the covariance matrix. And then this is the original count data one that I had that was equal to 0. And now when I look at the new one, it is a non-zero number. And so now I've put it into a space where hopefully when I am able to calculate all of the different PCA axes, they're going to show some kind of variance. And ideally, then I can use the two most important axes to put into a PCA plot in 2 dimensions. Does that make sense so far? Does anyone have any questions?
We have a request to explain what the evaluated determinant of the covariance matrix is.
Yes, I will try to do my best. I am not, I'm not like a statistician or mathematician, but the idea is that you're multiplying the matrix to itself essentially, because you need to measure the variability among all of the random points. So you have to multiply everything to itself essentially. And then you do a decomposition step in R, which that part I cannot explain exactly, but the point of those 2 steps is that first you're measuring all the variability among all the random points in your data, points being samples, and then the decomposition allows you to then have the outcome of that is having the Eigen Values, where you are able to see that variance. Does that answer your question a little bit? This is like primarily teaching our ordinations today, secondarily going over some stats. But I wanted to show you all the tools that I use to diagnose my data. And so I encourage you to look at some of the references that I list earlier and continue your own search of like how to best understand the inner workings of PCA plots. That's kind of what I'm getting at there.
Brittany in the chat window says yes, that answered your question.
Okay.
Can I also ask, with ILR, V11 is not an OTU, right? That is a ratio between some stuff. Is that true? My understanding is that ILR isn't a transformation of individual OTUs, but rather a series of ratios that reflect the data in the compositional table, right?
Yes.
Okay.
Yes. Yeah. Okay, so, but my data is transformed and now I can actually do the, I'll uncomment this right now because now we're going to work on actually visualizing this. And so here I'm using the principal component analysis or PCA command, and I'm putting in, not putting in my raw count data, I'm putting in my the log ratio transform data. And the output is a PCA object in R. And so what you can do with this is explore different components of your PCA output, and we'll actually use that to make plots in ggplot today. There are ways to use that as a PCA object and like plot it automatically, but I'm going to actually do it in ggplot so I can kind of show you the inner workings of that PCA object. So one of the other the main diagnostic tool that I use before doing a PCA to evaluate what my data transformation looks like, if I want to compare different data transformations, I can do this. But the other thing is to understand, okay, I'm summarizing all of my data into these axes, and I'm putting it in likely 2 dimensions. And I think most papers have a PCA with 2 dimensions. And I want to know if those 2 dimensions is giving my data, is justifying 2 dimensions. Meaning, is it doing my data justice? Is that the most appropriate way to show my data? And so I'm going to be using a scree plot for this, where I'm pulling out the standard deviation, which I'm going to do here. I'll actually execute this command now. So now in the PCA plot, and this is one of the reasons I like RStudio again, is that when I do that $, kind of like you're looking for columns in a data frame, it actually has different objects that you can explore. And in this case, I'm actually grabbing the standard deviation. And then if you want to know what those are, you can actually go over to the help menu and scroll down and look for what these values are. They're turning a class PCA, and this is the explanation for the standard deviation. And that's actually the square root of the eigenvalues. And so I'm actually going to pull out those eigenvalues and put them on a plot so I can show you the axes, the variance that I've calculated from my transform data. So to do that, I'm using this command that I've written. Again, it's using the tidyverse approach, where I'm taking my PCA analysis, I'm squaring it and making it a percentage as the data frame. So I'll execute that, and I want to just look at it really quickly so I can show you what it looks like over here. So now I have my different principal component axes, or the variance, and then I have the variance associated with each one. So now I can actually make a scree plot for this, which is I'm using the ggplot with that. So I'm actually going to zoom in so I can talk about this a little bit. So I think I've gone to length now talking about, now I have the percent variance, and then I have the PC axes here. And so these are all the axes that were calculated from my PCA approach. And the first one, right, is going to be over 25%. The first axis is going to explain over 25% of the variance that I see among all of my samples. And the second one is, closer to like 7 or maybe, 6 or 7%. And then the next one is pretty close to that one. So this is what I'm actually taking from this, or to show you, kind of give you insight into what I'm thinking when I see this, is that my data, the first axis is pretty good. It's actually showing a fair amount of variance among all my samples. But the second one doesn't show a whole lot of the variance among all of my samples. And the third one is actually really similar, and all the subsequent ones aren't too different, at least from the second axis. So if I plotted this in the PCA in 2 dimensions, it's only going to show the variance that's summed in these two. And so I have a lot of variance that is left unexplained. To expand on this a little bit more, I've actually written some fake data here that you can execute. So it's saving to a new object, a new data frame that's called Z. And so I just made up this data to kind of prove a point. But then if we plot it, okay, and I'll zoom in again, these are 2 examples to kind of elaborate on what I was talking about. So in the first scenario, in the top, we have these 3 axes. This is kind of an ideal situation of like, okay, this PCA analysis is most appropriately shown on 3 dimensions. And you'd be able to sum up a lot of the variation visually among all of your samples by showing the first 3 axes. Whereas this one, this would be most appropriate on 2 axes, where the first 2 would show a lot of the variance among all the samples, and then these other ones would not be shown. And so you want to make sure that the scree plot is a great way to diagnose the data structure that you're working with and see if 2 or 3 axes are most appropriate. Another thing I think about is that sometimes it's kind of hard to show 3 axes plots. I find them a little bit difficult to digest, but they can still be really fun to look at. So I'm going to go ahead and work on actually visualizing the PCA. I've talked about it for a while now. And so that's going to be this X variable here. And so if you look at this data frame really quickly, I have my samples listed as row names and then the PC axes. And I just plotted those when I plotted them previously, right? So this PC1 axis corresponds to here. And these are the values associated with that for each of my samples. And so I'm only going to make a plot that's 2 dimensions to start. And so it's only going to take PC1 and PC2 as the X and Y variables in my plot. So I'm using this approach where I'm taking this PCA object and pulling out those values. And I'm going to do some stuff to make this row names equal to a new column called time of day. And I'm just going to make it a little prettier, so then when I go into ggplot, the labeling will be all tidy, which is what I'm doing here. So like I mentioned, I'm showing this in just 2 dimensions, so I'm just pulling those values from PC1 and PC2. The other thing I want to point out here is that I did my X and Y labels using these 2 rows, or these 2 lines of code, where I labeled them PC1, and then I included the number from the variance data frame that I generated earlier. And so I want to take any questions really quickly. Anything?
Nothing in chat.
Okay. And so that's one of the main, so I wanted to go over the screw plot, and I showed you how to do a PCA. I'm going to introduce the next section, but there's a lot to uncover here, and I want to keep these lessons a little bit shorter. This will actually be separated into a second lesson as well. So I'm going to go a little bit further, but then we're close to finishing up here, and I'll finish up this code next week. So the next thing I want to talk about is doing the PCOA. And this is the principal coordinate analysis, which is doing a PCA, but then from a distance matrix. And so we actually need a distance matrix for that. And so here I'm actually relying on the vegan package. I'm using this vegan distance matrix calculation. And here I'm using first going to use a Jacquard distance metric. So I calculate that. And I want to take a look at the help menu here just to go over some of the options that are in vegan. And I think Jacob and Ella can comment on it, but the vegan package was really, I think there's a lot of tutorials now, but I recall that being like my very first like intro to R for my co-video ecologist or community ecologist. And so I definitely recommend looking over some of that base tutorial. There's a lot of neat features in there that appear in a similar form in some of the phyloseq stuff now. But right here, we're putting in a community data matrix of some kind, which I'm putting in my QC data. I'm not using the transform data. This is count data. And then I'm using a method listed here. And then the different dissimilarity indices that you can apply to your data are here. And today I'm going to use the Jacquard. And I start here sometimes, and then I compare a couple others. And next week we'll go over comparing some of them with stress, which we actually talked about last week. But I'm starting with Jacquard, and that's a little bit more like looking at the presence absence of your data. And so if you really want to look at that between different samples, this is a good place to start. And so calculating that, and then instead of the PCA command, I'm actually using the PCOA command here. So now I have these two objects that I'm working with. Similar to the PCA command, we now have this PCOA object that has a lot of options to kind of get into. I can list the values that are associated with this. So you look at values, now we actually have the eigenvalues listed, the relative eigenvalues. And I'm going to pull out these relative eigenvalues to again do another scree plot. Right, so this is the same data. I've done the Jacquard distance matrix on it, and done the PCOA. And so I'm going to use, this is this really similar code here to make another scree plot. And here we see that we again have, a lot of the variance is explained in the first axes, and then it's decreasing. Again, I'm not sure if the second and third axes are so similar to one another that, again, if we only show the data on these first two axes, I'd be worried that there's a lot of variance that is just not observed. And so I'm going to leave you with this last plot where I'm pulling out those variables again, and I'm going to try to make, or I'm going to make a three-dimensional plot using Plotly. If you've been paying attention to, or if you've been checking out a lot of the our lessons to date, I've pretty much used ggplot exclusively, but when I want to make a 3D plot, this is how I approach it. Here I'm doing the same approach where I'm pulling out the vectors. So actually, to actually make the plot, I'm pulling out a new R object called Eigen Values, where I'm taking the variances that I used to make this PCA plot, so I can pull out the percentages represented here as labels in Plotly. And now this is the command for the 3D plot. So some of these warnings come up when I do this, but I think it's a one-time thing. It has to do with packages turning over and having new commands for certain things. And Plotly is something that I actually more recently started using. And so it has a similar like a la carte thing as ggplot, where if you want to change a title for something, then you have to, I usually Google it or look up the help command for Plotly, and then you can modify these. I've even put in set one colors, and I've been able to set color to time of day, which is represented here. So this is the 3D plot component, and so we can actually see this is the big axis of variance, almost 50%, and the other two that are relatively smaller. And these are actually interactive, so you can start to kind of play around with your data and visualize what's going on. And I typically do this, especially when I see in the scree plot that there's 3 axes that are most appropriate, because ideally for talks and papers, I want to represent the data in 2 dimensions. But I think that this is still a really neat way to start to understand, like, what is the structure of your data, what clusters of things are starting to pop out, and you can kind of scroll over here. So I'm going to end with this 3D plot here, and I'm going to pick up next week by going over some other data transformations and continuing this like back and forth of like, okay, I'm starting with count data. This is the transformation I did. This is to diagnose what to do next in the PCA, and then work on also comparing the stress between 2 different approaches. So with that, I will take any questions, and I will pick up with Ordination's lesson 8C hopefully next week.